All right, so in this video, we're going to take a look at an example of what it is to fill out an energy bar chart, right? So let's take a look here. So let's consider the example where we've got a cup of hot coffee, and the cup of hot coffee is cooling as it sits on the table, okay? The first thing we want to do is we want to determine what is our system in this example. What is the substance that we are analyzing to see energy going into or out of? And in this particular case, we're looking at the coffee itself. Now, admittedly, I don't care for the fact that this says cup coffee because, again, we're really just focusing on the liquid inside of the container, not the cup itself, because the cup is a substance and it is absorbing energy from the coffee. So again, we really just want to focus on the liquid coffee that's cooling off inside of the cup, okay? That is our system, and that's what goes inside of this circle right here. Anything that is in the circle, that's our system. Energy is either going to go into the system or energy is going to come out of the system. And when we fill out this chart, we'll be able to kind of see that, okay? So the next thing that we want to do is decide whether ECH is going to be used. Now, in the video that I did, the part 1 of this particular series, I mentioned that the chemical energy is involved when there is a chemical reaction. If we go backwards, this is coffee that's cooling off. The coffee is not going to change into something else because it's colder. It's still coffee. It's just colder. So there is no chemical energy here because there is no chemical reaction here. So we don't have to worry about the ECH, okay? The EPH values, again, the phase energy, that's the energy related to our state of matter. So again, just ask yourself, if I have some coffee sitting on a table and it's cooling off, what is its state of matter before and after? You probably mentioned that the coffee is a liquid before and after, and that is the case. So when it comes to the phase energy, let's see, get my pen up here. So when it comes to the phase energy, remember we use 2 bars to represent a liquid, and I'm going to put that in the phase energy column, okay? I'm going to put that in the phase energy column, and we've got 2 bars to represent a liquid, and that's in the initial state. Initially, the coffee is a liquid. Well, again, like I had said, the coffee is also a liquid in its final state. So I'm going to add 2 bars of energy for the coffee. So again, before and after, initial and final, the coffee is a liquid. And that's why I'm using 2 bars for the phase energy, okay? Because in terms of phase energy, the coffee maintains the same phase energy. It stays as a liquid before and after, okay? Now, the next step is to figure out the thermal energy. Now remember, the thermal energy, or ETH, is related to the temperature. So in this particular example, what is going on with the temperature of the coffee? Well, again, the example that we were given said that, hey, the coffee is cooling down, so its temperature is going down, right? That should make sense. So when it comes to thermal energy, again, I'm going to use 4 bars of energy because I'm basically saying that, hey, my thermal energy in the initial state is very high. The coffee is very hot. It's got a lot of thermal energy initially. What about finally, after the coffee is cooled down? Excuse me. Well, I just need to represent that there are fewer energy bars. The thermal energy for the coffee goes down because the temperature goes down. Again, we started off very hot coffee. Lots of thermal energy over here. 4 bars of thermal energy. It could have been 3. It doesn't matter, okay? It could have been 2. It doesn't matter. But over here, we've got fewer thermal energy bars. Why? Because the temperature went down. And once again, the phase energy stays the same because all throughout this process, the coffee remains in the same phase, okay? And honestly, if I remember correctly, oh no, excuse me, there's one more thing that we've got to do. Now, basically, we total up the number of bars on either side, and then we see, okay, which side has more. So initially, we have 6 bars of energy, right? If I separate these, we just count them up. We just count up these bars of energy, and there's 6 of them, okay? 6 of them that we represented. Now, if we go over here to the final state, there's only 4 bars of energy. That's because the coffee lost thermal energy. The temperature of the coffee went down, so we lost some of our thermal energy. So here in the center, we just draw an arrow going outward. Okay, that's what we have here, this arrow right here. And then the 1, 2 bars of energy are leaving because again, we have 6 over here. We only have 4 on this side, so that means we are minus 2 bars of energy, just representing that, hey, the coffee has lost thermal energy because its temperature went down, okay? I want to say, I think that's it for this particular part. Yeah, exactly. We got to go to part 3, which part 3 is when we have a phase change. Remember, during a phase change, the temperature remains the same. So during a phase change, we are, as a matter of fact, let's take a second to add it here very quickly, just as a kind of preview. So again, during our thermal energy remains the same, right? Because during a phase change, the temperature remains the same. But during a phase change, our phase energy So again, during a phase change like melting, boiling, evaporating, condensing, those are all phase changes, our phase energy is changing. We're either increasing our phase energy by going from a solid to a liquid, or we're decreasing in the case where we go from a liquid to a solid. And in these instances, we'll have to use multiple energy bar charts to represent that change completely. But again, we'll do that in the next video. We'll just kind of pause it here because there is some practice that you'll be able to do based on this information, all right?